Okay, hello. My name's Nika, and this is UEFI and the task of the translator, using cross-architecture UEFI Quines as a framework for UEFI exploit development. Quick disclaimer, the views expressed in this presentation are my own and do not reflect the opinions of my past, present, or future employers. Viewer discretion is advised. So who am I? I am a security consultant at Leviathan Security Group. I primarily focus on hardware and firmware pen testing, and in my spare time, I like doing different UEFI projects, binary exploitation, skateboarding, learning languages, making art, and writing assembly programs. Greets to all of the following for all of their assistance and support with this talk. I wouldn't be here without them. Thank you to the team at Leviathan, and a big thank you to OffensiveCon for having me. Before we begin, I'd like to dedicate this talk to Sophia D'Antoine, a trailblazer, a world-class hacker, and a friend to so many in this community. Who recently passed. So let us all carry her legacy forward and strive to be hackers as elite and exceptional as Sophia. Format of this talk. This is a talk about translation. So in part one, I'll be talking about UEFI Quines, which are self-replicating UEFI applications in 3 different architectures: x86-64, ARM64, and EBC. Bless you. In part 2, I will cover the evolution of an SMM exploit from a simple chipsec POC to a standalone malicious driver. Okay, before we begin, there's some housekeeping notes on terminology because this is a talk about translation. So if you're sitting there and thinking to yourself, actually, does anyone in this audience know what EBC is or have any familiarity? I just want to get a gauge. Okay, sick. Yeah, I figured. Okay. But if you didn't raise your hand and you're just keeping quiet and thinking this to yourself, EBC isn't an architecture. It's a platform-agnostic intermediate language that leverages natural indexing to automatically adjust its instruction width to either 32-bit or 64-bit, depending on the host architecture. That sounds like ring -1 to me. I know, but we're going to cover it later, so we're just going to refer to it as an architecture right now, and we'll come back to it, so hang tight. And then terminology for ARM. If you're confused about ARM naming conventions, join the club. I'm going to be referring to it as ARM64 in this talk. Okay, so what is the task of the translator? In the context of this talk, the background that's required to know is that it's an essay by Walter Benjamin. And who is Walter Benjamin? He was a philosopher, cultural critic, and essayist. Other famous works of his included The Work of Art in the Age of Mechanical Reproduction and The Arcades Project. His essay, The Task of the Translator, was a seminal work in translation theory. And it is from this work that I'm going to be referencing and using it as a framework for understanding UEFI exploit development today. I'll be referring to this specific translation by Stephen Rundell. I don't speak German, so I've only read this essay on translation in translation, an irony that does not escape me. So, what is the task of the translator in UEFI in the context of this talk? In the context of this talk, it's a framing device for understanding how to write cross-architecture exploits. So the idea for this talk came to me because I have too many projects and I wanted to combine the work of them. And I realized that I could use the essay by Benjamin as a framing device for understanding how different projects of mine related to one another and related to techniques for exploit development in UEFI overall. So the 4 projects that were combined for this talk were exploit development research at Leviathan Security Group, my work for the Binary Golf Grand Prix, my work for the Binary Golf Grand Prix. I am teaching an OST2 class on ARM assembly, so that was my inspiration for doing UEFI exploit dev in ARM64. And then finally, I'm writing an article for VX Underground Black Mass on EBC. So how do we apply the task of the translator to UEFI? We can do this via two ways, or I did it via two ways. First was translating my winning Binary Golf Grand Prix entry from x86-64 assembly to two other architectures, which were ARM64 and EBC. And second, we can apply it by developing one exploit for an SMM callout vulnerability, and then creating new generations of that exploit and altering the technique that's used, or the language that the exploit is written in, or perhaps the architecture it targets. For an SMM callout vulnerability, that doesn't make as much sense, but other generic classes of vulnerabilities in UEFI, it does. But this leads to an inevitable question. If a goal of optimization is to eliminate redundancy, are we creating redundancy by repeatedly doing work? No, this isn't redundant work because, well, first of all, the UEFI apps already create copies of themselves, so I don't have to do that. But I aim to use translation as a mode. So, to quote Benjamin, translation's a mode. In order to grasp it as such, we have to go back to the original. So my goals with this project were to combine the research and knowledge gained from 4 separate projects and synthesize that learning. I'm always trying to further strengthen my UEFI reversing and exploit development skills. Translating my original self-replicating app from x64 into other assembly languages is one way to do that. Writing multiple generations of the same SMM callout exploit is another way to do that. So, how do we apply the task of the translator to UEFI? Here are some other notable examples to set the precedent for creating a new generation for a piece of art or an exploit. I consider them the same thing. So we have Crash. His original SMM backdoor was released several years ago, recently released a SMM backdoor next generation. Another example is Star Trek, with the exception of Leonard Nimoy, who's eternal. These are some research questions that I used to frame this talk, so we can keep them in mind. I'm just going to start with covering a brief intro to UEFI. Okay. So, in the beginning, there was legacy BIOS. And now we have UEFI, and everything's fine, and there's no more vulns, and secure boot wasn't just a marketing strategy for a feature that was never intended to be secure anyway. Just kidding. So UEFI is a specification that defines a platform-agnostic implementation for a platform firmware interface. Technically, when people talk about UEFI, they generally mean the UEFI PI boot process. So UEFI technically starts at the Dixie phase, whereas the PI implementation and the PI spec defines SEC, PEI, and everything preceding in this diagram. But for our purposes, when we talk about the UEFI boot process, we're kind of talking about the combination of UEFI, PI. UEFI is a replacement for the artist formerly known as legacy BIOS. A few things to note about legacy BIOS in relation to reverse engineering and exploit development. You probably all know this. It was written in 16-bit assembly, it ran in real mode. Legacy BIOSes were non-standardized IBV-specific implementations, which meant that they were very difficult to reverse engineer unless you had this book, and even if you have this book, it's really difficult to reverse engineer them because every single one is very specific. So Now we have UEFI, a rich ecosystem. It encapsulates such a breadth and depth of functionality. I'm just going to skip through this. Okay. Just some additional background in order to contextualize the talk. UEFI shell. The UEFI shell is an application. It's meant for interfacing with UEFI apps and drivers, as well as UEFI protocols. UEFI apps and drivers are primarily PE-COF executables, and a driver stays resident in memory, and app is unloaded from memory once it's done executing. Protocols. Protocols in UEFI are the keys to the empire. So in the way that in Linux everything is a file, these are essentially the meat and potatoes of UEFI. So the role of protocols is so integral to UEFI that there's a protocol is an interface that encapsulates data and functionality, and it's an integral part of UEFI. For every platform component, there's a protocol that defines an interface for hardware-firmware communication. One example is loaded image protocol. We can see that there's fields for data, as well as at the bottom, there's one method. So, to set the stage, true translation is transparent. It doesn't obscure the original. It doesn't stand in its light. But it rather allows pure language, as if strengthened by its own medium, to shine even more fully on the original. Okay, UEFI Generation 1, x64. There we go, sorry. So for those of you who don't know, Binary Golf Grand Prix is a challenge to allow programmers to make the smallest possible binary given certain constraints. So last year, the requirements were a self-replicating insert file format here, and it had to do the following, which was produce exactly one copy of itself, output 4, name the copy of itself 4, and not execute the copied file. So my methodology for approaching this was to write a valid working solution first in C to get a template. Then, using the C solution, I considered that my base text in terms of translation and translated that from C to assembly. And then I proceeded with golfing the solution, shrinking down the size of the binary, and finally reverse engineering, rewriting, refactoring the assembly, rinse and repeat until I could get it as small as I could with the given time constraints. So the initial size of the C solution was approximately 17,000 bytes. The final size of the assembly solution was 1480 bytes. My friend NetSpooky also came out with a recent solution that's 420 bytes, and he has a great write-up on it. Those are some tools that I used for the project. So I'm just going to go through my process for the program logic. To understand UEFI assembly programming, there's a few things that we need to do to set the stage. There's the handoff state upon program invocation, which gives us a lot of leeway to start. So here is the video of the base text that I wrote for this project. This is the initial C program. So you can see when you run it, it creates a copy of itself. It's outputting a lot of essentially print statement, debugging info to the console. And the size of the copy is the same as the original. So using this, I started with translating it to assembly. So this is the overall program logic breakdown. So remember how I said protocols are the meat and potatoes of UEFI. Protocols are what I'm going to be leveraging throughout the entirety of this project. So this whole chain begins with that first protocol that I mentioned, which is loaded image protocol. So we start with that. This is an example of doing two slightly different ways of the same thing, which is making a call to boot services handle protocol. We're passing in the GUID for the protocol that we want. We're getting a pointer to it. Loaded image protocol gives us information like the image size and the device handle, which we'll continue to use later on. We also use this for retrieving the simple file system protocol, which we can use to manipulate files on the file system, which in our case is FS0. I continue going through with the simple file system protocol that was just retrieved. I use the open volume method, open the root volume. Then using the root volume, we have two calls to open file. So we open the host file and the target file. Sorry. Okay, I think these slides got missed. Okay, yeah, sorry. There's one that got missed. So we have two calls to open file, and then we have a call to read, and we have a call to allocate pool. Allocate pool creates a temporary buffer. Read file reads the file into the temporary buffer. Usually this is an operation that takes two calls to allocate pool. In our case, because we used loaded image protocol to get the image size, we can Sorry, I'm so nervous. Okay. Okay. Oh my God, don't clap because I'm nervous, y'all. Oh my God, no. Okay. All right. So we use loaded image protocol to get the image size. Using that information, we know the size of the temporary buffer that we're going to read our host file into. That saves us having to repeatedly make this temporary buffer allocate pool, read file, allocate pool, read file. Series of two calls that is pretty standard if you don't know the size of the target or the size of the original image. So from there, once we have our pool, our target buffer allocated, then we write the buffer to the target file that we created. We continue with then freeing all of the buffers, or freeing the buffer and then closing all of the files. So we close our target file, our host file, and our root volume. So again, here's the complete program logic breakdown, in case that was a little complicated. Essentially what we're doing is getting a handle to the root volume. We're opening two files, our target file and our host file. We're creating a temporary buffer. We're reading in everything from our host file. We're writing to our target file. We're closing all the files. We're freeing the buffer. So none of this is really outside of the scope of, I don't know, file copying and Quines, but doing it in UEFI was a particular challenge. Oh my gosh. Doing it in UEFI was a particular challenge. The assembly programming itself was not that difficult just because I have a lot of experience with assembly programming already, but understanding the calling conventions and understanding how to do specific things within UEFI was a lot trickier. So for example, a lot of calls, or pretty much every call, will require the passing of a unique GUID, which identifies the protocol that you are trying to locate or handle or retrieve. This process in assembly was a little tricky, but eventually I got it. So this was just using the stack. You can see on the right here. In addition to the difficulties with the assembly, the next part was golfing the solution. So this involved removing unnecessary libraries and dependencies, using the UEFI ecosystem, and binary mangling. PE binary mangling I had no experience with prior to this project. So again, thanks to NetSpooky, here's his guide on PE binary mangling. And then finally, one of the golfing tricks that I used for this was just understanding some of the ways that UEFI has wrappers around different protocols or different methods. So open handle is just a wrapper around handle protocol, or that should say open protocol versus handle protocol. Open protocol is a wrapper around handle protocol. It just takes 2 extra parameters. So if you understand this and you know that you're going to be using handle protocol underneath it, you can save a few extra bytes. Here's the video for the, oh my gosh. We had last time. Okay. So, UEFI Generation 1, what did you learn at school today? So, leveraging the UEFI ecosystem by walking from protocol interface to protocol interface allowed me to better understand UEFI internals and build a base knowledge for building better exploits. This also made doing more difficult techniques or implementing more difficult techniques with exploit development a lot easier, and knowing how to identify certain data structures or protocols or even offsets for desired methods within protocols. An example of this, this kind of application is building ROP chains for SMM exploits. And it also gave me new knowledge of PE binary mangling, which I had not had any experience with prior to this project. And then finally, one thing that this project gave me was new knowledge of how to write UEFI shellcode. So if you don't already enjoy doing assembly programming, you probably know that it's an essential skill to know how to write shellcode, or at least for reverse engineering, having a better understanding of the assembly and how the constructs work. So this project gave me a very big leg up on that. Okay, so to bring it back to the idea of the task of the translator, the translator's task consists in this: to find the intention toward the language into which the work is to be translated, on the basis of which an echo of the original can be awakened in it. So this brings us to our second generation, ARM64. Okay. With the second generation, this wasn't an entry for BGGP. So what were the goals of this Quine? What were the goals of this Quine? I wanted to confirm that a Quine was possible on ARM64. So that was the first. Then knowing or having confirmed, so this was a big if, but having confirmed that, I wanted to translate the original to a valid working solution in ARM64 assembly. This would be just good practice for me with getting better ARM64 exploits. And again, since I'm teaching this OST2 ARM assembly class, it would give me more experience with making small demos or creating samples for that class. And again, the process of golfing doesn't necessarily strictly apply to challenges like binary golf Grand Prix. Golfing is a really good way to understand how to optimize for size, especially when you want small shell code. So again, advanced mastery of ARM64, practice shell code writing, and better understand the nuances of UEFI, RE, and exploit dev for a different architecture. So I started with just recompiling my valid working solution in C with an ARM64 toolchain under the EDK2 build system. This was perhaps the first time the EDK2 build system came through for me. It's notoriously such a pain to work with, but this one did. Then using the C solution as a base text, I started translating that. So moving from the C source to, or rather, the disassembled and decompiled C binary, originally C binary, to assembly, reverse engineering it. And then, again, reverse engineer, refactor, rewrite the assembly. I have here the task of the translator is to be a cross-compiler, but we'll come back to this. But before I started with step 1, I wanted to start with step 2, which was a bonus step. Since I hadn't written any UEFI applications in ARM64 assembly before, I started with a Hello World ARM64 assembly program. So, again, this is just an example of the handoff state for a UEFI app or driver EFI image under ARM64. It's very similar to x64, just different registers, obviously. But using this base information from the program invocation, we can, again, do that same walking the chain of protocols and building up the entirety of our program logic and our final working exploit. So, okay, I guess that video. The video is, it runs, the original has a size, the copy has the same size, it prints debug info. Ta-da. Okay, so as I mentioned, there's this question of, is the task of the translator to be a cross-compiler? We can come back to Benjamin on this, and to quote Benjamin here, in reality, with regard to syntax, word-for-word translation completely rejects the reproduction of meaning and threatens to lead directly to incomprehensibility. So if we go through and try and look at each line in the original x64 assembly and translate it to ARM64, we're not going to be able to get a complete working solution just because of the large differences in how architectures implement different functionality and do different things with the stack. So the better way to approach it is to think about programming idioms in each assembly language, and from there, look at base blocks that we can translate from one architecture to another. In these slides, I just have a couple examples of different, I would consider this an idiom in ARM64. And this is just a view of Ghidra using 2 UEFI-specific plugins for looking at, again, the base text, which is the C cross-compiled ARM64 binary. So on the left, I've just added a box to highlight the process for loading the GUID. Like I mentioned, loading the GUID is just, it's very finicky, but I liked this on ARM64. It's fun. You have like the fun combo with the barrel shifter and the immediates with the moves. I just think it's nice. But yeah, a lot of my process consisted in this, of looking at it in Ghidra, understanding how it was re-implemented in the disassembled and decompiled version, and sort of using that as a secondary base to start reconstructing the ARM64 assembly file. But again, you can't go word for word on the translation from this version because it's not going to end up being comprehensible, but it's a good template to work from. These are just some of the tools that I used throughout the development process. As I mentioned, as I mentioned, the build system that I used initially just to get the working version from the C source file was the EDK2 build system. Eventually, I switched to using a makefile to cut down on a lot of the extra bulk and fluff that comes with the EDK2 build system. But that is a bit of a process that we don't really have time to get into, but and then finally, debugging. This was just something that I didn't have experience with on ARM64 for UEFI debugging. If you've done anything with UEFI before, you know that the process for getting things loaded into QEMU and GDB specifically, again, this is doing testing in emulators, not on hardware, is a little bit finicky. On ARM64, the documentation is a little bit more sparse, but I was able to get it working. So this was through the use of the QEMU monitor, combination of a serial console, and then computing the offsets for the entry point manually rather than using the debug log. Okay, so we come to our end of school day. What did you learn? Again, this is a process of learning more about the UEFI ecosystem by walking from protocol interface to protocol interface. It's helpful for building wrap chains, but it's also good for understanding UEFI ARM64 implementations in general, where the documentation, again, as I mentioned, not just for debugging, but overall is a little bit more sparse, in my experience. And again, knowledge of how to write UEFI shellcode for ARM64. Okay. Finally, generation 3, ABC. Why ABC? ABC was a natural fit for the last part of this project because of its inherent variability and malleability. So it uses natural indexing, which I'll get to in a minute, but the spec for EBC and the initial idea for EBC was to become something of a Tower of Babel. So its design goals were to be a platform-agnostic architecture for PCI option ROM implementations. So rather than every IBV implementing an architecture-specific implementation for an option ROM, the idea was to have a sort of universal language for them all to converge on. This was the idea for EBC. So EBC is an intermediate language. It's like LLVM bytecode or Java bytecode, or insert your favorite bytecode there. It's run in the EFI bytecode virtual machine. So, So if a compiler is a translator, EBC could be considered something like the Holy Scripture, per Benjamin's metaphor. So, for to some degree, all great writings, but above all, Holy Scripture, contain their virtual translation between the lines. The interlinear version of the Holy Scriptures is the prototype or ideal of all translation. It's a little bit heavy for EBC, but just stick with me here. So I really liked the idea of EBC. I thought that this platform-agnostic implementation for PCI option ROMs was really cool. There was a lot of meat to it that appealed to me from a malware development perspective, especially based on other work that I had seen that leveraged virtual machines and bytecode in terms of creating metamorphic engines or polymorphic engines. It seemed like there was a lot there to work with. I'm going to cover a little bit of the architecture details first, and then we're going to cover more about the next steps with EBC. So the EBC VM has 8 general purpose registers, and then it has 2 dedicated registers, an instruction pointer and a flags register. It uses natural indexing, which uses a natural unit to calculate offsets of data relative to a base address, where a natural unit is defined as the size of a void pointer. So this is the mechanism by which EBC can run the same on 32-bit or 64-bit architectures without changes to the EBC C source code. It's compiled, and then it's run in the EBC VM. And the EBC VM is responsible for implementing this switch between different architectures. So it sounds great. If it's so great, why haven't I heard of it? Well, there was only one compiler specifically designed for EBC, which was the proprietary Intel C compiler. Formerly, it was sold for $995. Now you can't find it on the Intel product site. It just redirects to this page. If anyone has a copy of it that they would like to lend me, please let me know. There are a few open source options available, but there are a few bugs with them, and for the most part, a lot of the initial momentum with EBC seems to have died out. It's no longer officially part of the spec, but it is included in the spec. There's an entire chapter of the UEFI spec dedicated to this, but it's a feature that is rarely used, and as a result, and largely, I believe, due to the high price point of this Intel proprietary C compiler, there are very few in the wild reference images for EBC. Okay, so you might be wondering, if EBC is a dead ISA with little to no reference implementations, why am I talking about it? Well, what if there were legacy or deprecated features that were lingering in a code base for years? And what if IBVs or OEMs were slow to patch platform firmware and remove legacy features? Well, that's the case here, because there's still the EBC interpreter in the Tiano Core EDK2 main branch. Just because so this feature is there. It doesn't mean people use it, or it doesn't mean that it's frequently leveraged, but just because this feature is hardly used by the majority of IBVs or OEMs doesn't mean it can't be leveraged by someone who wants to dig into it a bit more. So this is part of an ongoing project, so more of my work on this is going to be coming out in the next few months, but I thought it was an interesting, strange, archaic architecture to talk about, and the connections between legacy and deprecated features leading to high severity vulnerabilities has a pretty strong track record, especially in platform firmware. So the fact that this still lingers in the code base kind of piqued my interest. Here are just some of the additional RE and development tools that I've been using while working with EBC. UEFI exploit dev. Oh my gosh. This is a quote by the great Vincent Zimmer from his blog post on the EFI bytecode, which is an excellent read, by the way. It speaks to the vulnerabilities that I find often when I am working on UEFI exploit dev. So UEFI exploit dev. This second part of the talk is going to do a bit of a pivot. So how did I get here? My research on UEFI exploit dev began after I kept running into the same problem at work. I was finding UEFI vulnerabilities, but I didn't know how to write exploits for UEFI. So this part of the talk is an overview of my experience learning UEFI exploit dev. It's ongoing, and I welcome feedback, and I'm here to learn just like all of you. How did I learn to write UEFI exploits? It is a two-part answer. The first part is reverse engineering and replicating the techniques of other POCs. So translating POCs, if you will. And the second is learning about UEFI by writing apps and drivers. So the process of doing the binary golf Grand Prix challenge, doing these different versions in different architectures was a big component of that. It was a way to understand how UEFI internals worked and how to write assembly code and therefore shell code for different UEFI targets. Reverse engineering earlier malware or POCs. So how does one start writing an exploit for a new system or an unfamiliar target? You understand the target. So in my case for UEFI, it consisted of this. You build a foundational knowledge, RTFM, read the holy trinity of UEFI exploit dev and UEFI requisite knowledge, which includes the UEFI spec, beyond BIOS, and rootkits and bootkits, in my opinion. There's a lot of other great material out there, but for me, this comprised the core of the foundation that I built. Second, find previous notable work in UEFI exploit dev or UEFI malware, and then read and then reread the base text. And then translate the base text, meaning try to apply the same exploit technique that a previous author used on a new vulnerable target. So one example of this, which I'll cover shortly, was I looked at Crash's SMM callout POC for a vulnerability in a different driver as a template for writing an SMM callout POC for the vulnerable driver that I found. So in my case, it was IDE bus Dixie. Crash's was a different one, but it was the same template for understanding how to start writing an SMM callout POC. So there's no ROP Emporium for UEFI specifically, and there are very few examples of UEFI-specific CTF challenges. There's a notable one that I'll come back to in a minute. But there are good resources for learning all of the skills you'll need to write UEFI exploits. So my perspective on this is no exploit dev roadmap. Honey, that's what I call a make your own adventure CTF. So make your own adventure CTF. These are some really good resources that I used for building up that foundation. So that's all good for theoretical background. Let's get to just some practicals of digging into SMM callouts. So started from ring -2, now we're calling out to an attacker-controlled region of memory. Here's an SMM callout. Who sees it? Okay, so I'm going to show you how to see it. So you found an SMM callout vulnerability in a combined SMM Dixie driver. Now what? These are just some framing questions that I used to guide my process when I started this. Very quick background on SMM. For those of you who don't know, it's the most privileged processor mode for x86. Processor enters SMM only when an SMI, or system management interrupt, is invoked. SMIs have the highest priority of all interrupts, higher than NMIs, and SMM is meant to act as a privileged and separate processor mode for handling critical system functionality. So SMM code and data, because they're so important, reside in a different region of memory called SMRAM. It's meant to be protected, and it's meant to be locked during platform initialization. It should not be reachable by code that's running in kernel space or user space or anything outside of SMM. But you might be wondering to yourself, okay, we have this separate and isolated processor space. How do we invoke an SMI if SMI handler code is in SMRAM and SMRAM is a theoretically protected region of memory? How can we invoke an SMI handler with necessary arguments if we're outside of SMRAM? How are mirrors real if our eyes aren't real? The communication buffer. Technically, there are multiple ways to facilitate SMM and SMRAM and non-SMRAM communication, but this is the one defined in the UEFI PI spec. So the communication buffer is part of the UEFI SMM communicate protocol. It defines a means for communication between non-SMRAM and SMRAM. The communication buffer is located within this data structure called the SMM core private data structure. It has a signature of SMMC that you can easily identify if you look through a memory dump in the UEFI shell and search for the string, which I'll get to in a minute. And the UEFI SMM communicate protocol requires that the SMM communicate buffer is set up in a very specific way with these fields. Okay. Then an SMM callout. How does this happen? When code that's running in SMM reaches out to a data structure or code that's located outside of SMRAM, this is the necessary conditions for a callout. So two very obvious examples that come up again and again are SMI handler code that calls out to a function that's in either the UEFI runtime services table or the UEFI boot services table. Code in either of these structures can be attacker controlled. Why should I care? This should be obvious, but if you get code execution in ring -2, it's a pretty unprecedented level of firmware persistence. Okay. The different components of an SMM callout, I'm going to just go through these from our previous slide. So we can see at the top, we have the code for an SMI handler. It's executing in SMRAM. We have a set of necessary conditions for a certain code path that will be reached. None of this is bad so far. And then at the bottom here, we have the SMI handler calling out to a function in the UEFI boot services table. So this is the callout. So the SMI handler is making a call out of SMRAM to a function in the UEFI boot services table. The boot services table can be attacker controlled. The whole methodology for this process is essentially overriding a function pointer. It seems very obvious, but it's for me, it was a little bit tedious or a little bit difficult to get started, just because how do you override a function pointer in the UEFI boot services table? How do you get access to that? How do you find that in memory? How do you know where that is? There's different ways to do it. One of them is you can use built-in functions within the UEFI boot services table already, like get memory map, and then use that information to grep through, basically. The next part is determining the SMI number that is triggered or that needs to be triggered in order to invoke the specific handler function. You allocate space for your shellcode, you overwrite the function pointer, you trigger the SMI, shell gets executed. Okay, so it seems pretty easy. For version 1, the premise that I considered was start with ChipSec, which is the platform firmware security toolkit. It's pretty much the de facto standard for writing a lot of POCs. It makes things really, really easy, templated out, and it abstracts away a lot of the nitty-gritty of the underlying UEFI functionality. So, didn't really work on an M series MacBook. So, which makes sense because ChipSec is a platform security toolkit created by Intel. So it's a really cool open source project, but I was not able to get it to run on the machine that I was working on, and I had a limited amount of time to write a POC. So rather than just picking away at it and trying to reconfigure things, I just went back to the drawing board. And I looked at what's going to happen if I just try and re-implement the part of the ChipSec functionality that I want to leverage, which was basically just this function, this SWSMI function. So there were no binary exploit mitigations present in the vulnerable driver, and I felt like there was a straightforward path. So I just went ahead and updated the methodology. So remember how I talked about the communication buffer earlier? Triggering the SWSMI using the identified number is now broken up into this smaller series of steps. You set up a communication buffer, you make a call to the SMM communicate protocol, and then you write to I/O ports B2 and B3. So this was just leveraging, again, those built-in functions in the EFI boot services table that I mentioned, like get memory map, and then searching for regions of, or address ranges that were a specific type. So in this case, I wanted to find address ranges that were of type EFI runtime services code or EFI runtime services data. This is because in order to make a call with the communication buffer, they have to be either of those two types, EFI runtime services data or EFI runtime services code. So I wrote up this PSC, I had everything ready, and then sadly it got bricked. So I found this vuln when I was on a time box pen testing engagement at work. I wrote my first two versions of the POC, I was ready to try it, and then my colleagues found a different vuln that they wanted to write an exploit for it and test. They did, they successfully exploited it, and it bricked the machine. So the client was happy, we got some really cool high severity findings, but unfortunately I wrote a POC that I haven't tested yet on real hardware. And more importantly, I don't have a demo video for that. This is just, I think, a sad reality of sometimes working in hardware and firmware pen testing, is that you're going to brick things, and sometimes you brick things during time-boxed engagements. And, but the learning that went into this is still applicable, and I've been able to use it for subsequent work. Additionally, testing and emulation for SMM callout vulnerabilities, in my experience, has been a little difficult, so I've shifted to doing more of a hardware-focused debugging and testing approach that I'm not going to cover today, but there are a lot of other good resources for that will be at the end of the slides. Finally, just for looking at other options for testing it on real hardware, it's present on these other Fujitsu Lifebooks. I found a vulnerable version of the firmware on the Fujitsu website. I confirmed it was there. But trying to find one of these Lifebooks wasn't feasible. It was pretty much just sketchy Craigslist ads. So rather than trying to find the specific piece of hardware for the specific BIOS with the specific vulnerability, I decided to go with something a little bit different, just to give you all a way to get started in this. So that's just the example of the vulnerable firmware version. So, as I mentioned, there's no ROP Emporium for UEFI, but there is, in my experience, scouring the internet for these, there is one CTF challenge, and it's really good. So if you want to get into this, go solve the CTF challenge. It's really cool. It's got 3 levels. You have like no mitigations, 1 mitigation applied, 2 mitigations applied. This is a really good testing environment if you want to practice writing SMM exploits. You can also practice doing some basic bypass mitigations for things like SMM code check EN, which I do not have time to cover, but it's in the slides. So, yeah, I don't have time to cover this, but and these are just more tips and tricks for guiding your UEFI exploit dev. I'm gonna just end on this. Okay. Sorry, I'm realizing we're running over. I love UEFI. It's my favorite. UEFI exploit dev is great, and it's fun, and there's a lot of space for creativity and flexibility and trying new things. There's also mitigations that are common on modern OSs that aren't present in UEFI or not consistently applied. It's a really cool space for learning and for research, and I think you all should give it a shot. So, just to end, here's a Benjamin quote to pull it all together. Just as fragments of a vessel, in order to be fitted together, must correspond to each other in the tiniest details, but need not resemble each other, so translation, instead of making itself resemble the meaning of the original, must lovingly and in detail fashion in its own language a counterpart to the original's mode of intention, in order to make both of them recognizable as fragments of a vessel, as fragments of a greater language. Okay, that's it.
First of all, thank you for your talk, very interesting, has great hack value, appreciate. And my question is about EBCVM. I'm wondering what privileges EBCVM typically runs with, or maybe this actually varies between firmware, because without this VM, when native code is implemented in option ROMs, it's run on the CPU, so the firmware has to invoke it with appropriate privileges, or there would be vulnerability. But EBCVM, theoretically, I'm just thinking, might be running with different privileges because firmware authors thought that it's sandboxing essentially what's an option ROM. The instructions could be somehow limited. Have you studied this maybe?
Sorry, so you're just asking about like where the different ways that the EBCVM can be implemented or where it can be run, or was that your question? Is that kind of, or sorry?
Well, as you have mentioned in your talk, there are different privilege levels, at least SMM is most obvious. I would seriously doubt that EBCVM would somehow run in SMM mode, also that would be fantastic for exploits against the VM implementation. But I'm suspecting that there could be other privilege boundaries, not so harsh as SMM maybe, or maybe some kind of attestation break if the code in option ROM was assumed to be running in a trusted sandboxed environment, but it is not. Maybe a topic for research, I don't know, or maybe this is just nothing.
Yeah, I'm not entirely sure. I know that there are different implementations in terms of the open source EBC. So one of the examples is there's an EBC VM that can be run in user space. So it's technically just like a an emulated version of it. I don't know specifically what the restrictions are in terms of authorization and boundaries for EBC and EBC VMs. I don't have a definitive answer, so I don't want to give you wrong info on that. But it's definitely something worth looking into more, and I am. So I'll follow up.
Thank you very much.
Thanks.